Thanks. So this was around the construction phase support on HS2 Earthworks. So I've not been part of the design. I've been mainly working in the northeast of England, around Yorkshire. And so it's interesting to come down and see something quite different. So on this one, presentation, quick introduction, where's the particular site that we're looking at? So it's focused around the particular site, Park Lane cutting. Then look at different aspects of the geology and how it influenced the review of the ground model. So there hasn't really been any further design work based on the ground model, but it helps us to understand things during construction, because everybody knows when you're looking at the development of a project, the majority of costs can be saved at that optioneering and early design stage. Then things get refined as you go along. But on long-running projects, there's opportunities to look at whether further savings can be made from the people on site, not just there to catalogue 5% over of what the earthworks that have been done. So one thing that struck me when I came down to site was the shape of the gravel. Because most of the sediment around here is meant to be glacial fluvial, and that doesn't look very glacial fluvial to me, but I was told that it was. So what found within looking in the cuttings is that we had these laterally discontinuous layers of different types of sediments, and they were not necessarily causing issues, but they led to let's say some program challenges. And so this was how we looked around that. So refinement of ground models, as I've just said, that as you go through a project, then your design model gets simplified to go into numerical analysis, and they go on site. And within this type of glacial margin, then things aren't always as straightforward. And can you take advantage of that? So Park Lane cutting, it's just southeast of Birmingham, between Birmingham and Coventry, just north of Balsall Common. And it's adjacent to a little village called Bradnock's Marsh. Remember that name because it appears on a lot of the BGS cross sections, and so you can reference yourself from that when I put that up. What does far sight mean to people? When you're thinking of, you're trying to understand where you are in a sequence. Somebody tells you to go to a site, you go there and cutting is open, but where actually are you in the in a terrain model? Do you know? And been very lucky with Gibson last year, oh, sorry, 2 years ago, divided the area up into Birmingham Plateau and the Warwickshire and Avon rivers, and our site's just on the border. So just another view of the site. There's a laser pointer. Oh, here we go. So this green line is the A452 dual carriageway. Runs on a ridge. You see that you have got the River Blythe system to the west. There we go. And then you've got another watercourse on the east side called Horn Brook. So when I mentioned about that far site and looking at all the different river systems that are around and all the different watercourses that come into it, how did they form? And are they important? Not important. So just on this one, not easy to see, but just on Horn Brook, there's a series of faults. So that's why Horn Brook's there. But there's none around the River Blythe. So how did the River Blythe form? So Park Lane, thematic view of part of the digital terrain model prior to the excavation model going in. So you've got the high ground to the southwest, where you've got Borsal Common. You've got the A452 that runs along the ridge between the two watercourses. You've got the HS2 alignment that's further to the east, but just trying to keep out the water. There's only around 13 meters difference in elevation between Borsal Common and the lowest point as you go down to the River Blythe. So when you look at the DTM, there's not a right lot of variation in it, but one thing that did stand out was that there was a series of gullies that were almost perpendicular to the ridge. So how did they form? Are they significant or not significant? That's just the illustration of the gullies, but you can see that there's quite a change of slope at the alluvial part of the floodplain there. So bedrock, when you're not quite sure what's going on, then you go back to the beginning. So in this case, somebody made an offhand comment to me in one of the compounds about Brunter pebbles. And that kind of got me thinking, because when I'd read the memoir, it said that most of the gravels in the glacial fluvial deposits around this area came from North Wales. So things don't quite stack up. So I went back and looked at the Syria guide and the BGS engineering geology on Mersey mudstone, and it illustrates how Mersey mudstones formed. So you've got the larger Pangaea continent about 325 million years ago. Then you've got the Variscan orogeny, and then the outwash from the mountains, Variscan mountains, flowed northwards into the Warwickshire Basin and further north. And as that developed over 50 million years, you got the change from the sandstone being deposited, the Sherwood Sandstone Group, more to the Mersey mudstone through flash flood sheet deposits. And so that thing about Brunter pebbles, Chester beds, how different are they? So from the publications, most of them came from Northwest France, from the series of the volcanic series in the, I'm not going to say it, Amorcian. Somebody could probably tell me. There's plenty of people on HS2 who are from France. I should have asked one. Anyway, most of the pebbles within the Triassic sandstones came from this Northwest France. So glacial environments. I love the BGS onshore index. There's so many different layers within there, and one of my favorites is the quaternary section, and that contains the map of the glacial domains. Because when you do glacial geology on your degrees, you generally you're generally looking at valleys, the glaciation in valleys, and terminal moraines and eskers and kames and various things. But really, as you can see there, there's quite a few different glacial domains within the UK, and there's some larger areas and there's some smaller ones. And our area is in this bisected till domain, but then just to the southwest, we've got the minimal superficial deposits. Why does that matter? And is it right? So everybody knows that on a 1 to 50,000 scale map, that any geological boundary is at least plus or minus 50 meters. And when you look back through the series of how geological maps have been developed, and you look at the original hand-drawn ones, you see there that it's just somebody's interpretation. So you've always got to keep an open mind. So I'm used to working in the Vale of York, which is a lowland basin domain. So glacial geology on the east of England is quite different to the west of England. I thought because I worked on the Vensian margin in the Vale of York that I knew all about the margin. But again, that thing of this whole thing is go back and read the books again and try and understand where you are if it doesn't make sense. So I've also worked in the plateau and valley domains in South Wales and northwest of England, worked in the dissected valleys in the southeast and east of, and the superficial dominated domains in the northeast, where you've got quite thick glacial sediments. So according to the main map there, we're in the dissected moraine. But the one that actually makes more sense is just move southwest, and we're more in this minimal cover because there's plenty of places where there's no superficial deposits, as in no transported superficial deposits. So that's just that boundary probably needs to be modified. So that's one of the things that perhaps the HS2 work can do, is provide a bit more information to the BGS to get them to reconsider that particular layer. So mid-Pleistocene, that was another surprise. So generally glacial fluvial deposits, again, I think know what they are because I've worked in glacial valleys, short transportation, so more likely to be angular, subangular. But down here, as I showed from the first photograph, they're all rounded. So that's why I went back and started looking, well, where does rounded gravel come from in this part of the country? And so in Triassic sediments, it comes from France. So we're in the Albion glacial group, but the reason why I put the other map up on the left, mentioned about the River Blythe, and you've got the Proto River Blythe just in that area. So I wondered what effect that had on the shape of the topography around where I was. So mid-Pleistocene, that's a pretty long period. Kind of covers from 0.78 billion years to 0.12. So what does it actually matter? Well, within that period from Devonsian to Anglian, you've got two interglacial periods where there's no ice. So you get peat deposits. So I'm next to two rivers, and that River Blythe was formed well before the Anglian. So am I going to get peat deposits between my two watercourses? Because when you start to move on to that's just kind of going back to the far side part again, just about the two glacial limits. Skip that one. So superficial deposits, haven't switched bedrock on. So you can see that when I talked about the different glacial domain, here it's kind of 50-50 between whether I've got bedrock or whether I've got superficial. And at this point, just off the southern end here, I'm starting to go into the Warwickshire Avon system. Who uses paper maps anymore? Who uses paper 1 to 10,000 maps? 10 points to you. They don't put it on the 1 to 50,000 maps for some reason, but they still put it on all the 1 to 10,000 maps, which is great. And it says, don't trust what we tell you. This is our best interpretation of all the knowledge that we've got, but it could be completely different. And so that's why you've got to keep an open mind. So that thing about when you're on a long running project, somebody's done a desk study 10 years ago, and it goes through a number of companies and it gets simplified. And they're looking at all the great GIS systems that are put together on projects, and they're looking at the onshore index and all sorts of things. But it all comes back to some person who walked around a series of fields looking in drainage ditches and any excavation they could to interpret what they thought might be going on. So it's always having that in the back of your mind. And so that's the thing that confused me here. So where are we? Park Lane in this sort of area. Bradnock's Marsh again around here. And you see all this other lovely sequence to the southeast. And the brownish colour is the interglacial period. So there's been a break there between the Anglian and the Woolstonian just over the hill. And you've got a bit of here lies dragons on my side of the hill where they're not quite sure. So they've just put a few indistinct dashed lines with some question marks. Yep, you might get some glacial till, you might get some interglacials, we don't know. So unless you question that, I'll just go back a slide actually. Just in here, they've handily put in the glacial domain, the dissected till domain, but you see there that there's no till. So again, people making their best interpretation with the information that they've got and the time that they've got to do it. So with that in mind, that we're somewhere between the Vensian glacial limit and the Anglian glacial limit, and we've had the Woolstonian in between, then we're going to get a periglacial environment. So we all think about ice advance, but a lot of the geohazards are created by the ice retreat. And so in this case, we've got 3 deglaciations to consider. And Merton and Valentine were great to put this together just to show the different likely geohazard areas that you might get from the different periods of ice retreat. So everybody's favorite, solifluction. And that's just an example of what it might look like on a shallow hillside. As you know, solifluction can happen on quite shallow slopes at 5 to 10 degrees. And as I mentioned on our site, you've got just quite a shallow slope angle, and we might have those interglacial deposits, so we might have some peat in there. What's going on? Don't quite know. So looking back at the quite high resolution DTM, there's no features that indicate any sort of scarring from soliflucted slides. And because we're in that glacial, we're not, as in the Vensian glaciation didn't wipe out any scars that could come from the end of the Woolstonian, then I'd have thought I might have seen them. But we have got these gullies coming down from the ridge. Somebody gave me a really good piece of advice about the development of transport infrastructure in the UK. Canals came first and chose the best ground and got the best alignment. Railways came second, got the second best ground. Roads, as in motorways, came last and generally had to avoid all the conurbations that were built up around the railways and the success of the Industrial Revolution. But people weren't stupid either. For the main roads, they always kept the high ground, so to avoid the flooding. And people built their towns on the high ground, as in Balsall Common on the top. But HS2 gets given the most challenging ground. So you're going through odd areas. And so there's lots of viaducts going over these different watercourses. But it still concerned me that I'd got these channels, shallow channels on the side of the hill. What did they contain? And as you saw there, back on the periglacial chart, we're in zone 4 where we've got 4 periglacial periods, 3, that are likely to get pattern ground from ice wedges did we find any? Well, image on the left-hand side, that Park Lane cutting goes diagonally across parallel to the A452, just in there. So there's no patterns in the field. So when we did excavate, and we did get into more of the glacial lacustrine soils, we did find discontinuities within the soil, which is highly unusual because generally you don't get any form of discontinuity patterns within soil. But pattern ground related to periglacial particularly affects silt. So when you've got silt, you get thermal contraction, and that causes the discontinuity patterns. And in this case, they were around 2 to 500 mil spacing, the full height of the silt. And if you undermined it, then the ground would generally fail against that. But if you think about you doing a cable percussive borehole or any form of dynamic sampling through that superficial deposit, you're not going to pick up that structure because all you're going to get is the bag. So you don't actually know whether there's structure there until you go in. So we've got a couple of structures. We've got the vertical contraction cracks, tensile contraction cracks, and the thaw shears. And so the red soil, just kind of think about it, what it's from. It's probably Mercia mudstone that's been eroded and deposited. Red colour, probably a laterite. So thinking back again to where laterites are deposited before they become rock. So that kind of fits in where the UK was around 20 degrees north when we were in Pangaea. So within, just on the edge of the tropics, where laterite soils can develop. So going back through that sequence of what our local rock's made of, where were they, what's the genesis of that sediment before it became our sedimentary rocks, keeping all that sort of thing in mind about how it might then behave when it goes through a periglacial process. So that was the thing about not be wary of silt, but any silty soil is a lot more prone to getting pattern grounds forming within it under periglacial processes. So those discontinuities that we saw were the precursor to ice wedges. So I was looking out for whether we'd got any infilled ice wedges, but we haven't found any yet. So what does that mean to Park Lane cutting? So just reminding you back of where we were. Have we got any interglacial peat deposits? No, we didn't find any, but we did find glacial till. And we're quite different just to the ground to the southeast, where you've got that quite interesting sequence of glacial and interglacial sediments. So our site, where the arrow is in the centre of Lake Harrison. So Lake Harrison was formed by the terminal moraine just down there at Mott, just in the southwest. And again, me thinking that I knew about the glacial lakes because I'd worked in the Vale of York. It's quite a different form of glacial lake. So you don't get those laminated fine clays that can cause quite a lot of problems of slope stability, where you've got varved sediments where it's settling out during the year. Here it's quite different. They're generally deposited in flood events. So again, quite handy that Gibson 2 years ago went round and did luminescence modelling of the sands in Meriden quarries and one near Bicken Hill at Park Farm. And the sediments there were around 180,000 years old. So it kind of fits into that Woolstonian period of glacial deposition. So we've got a Mercia mudstone laid down over the top of the Helsby sandstone in the Triassic period. There's some faulting, as we've seen around Holmbrook. Then we've got some erosion. Let's say it happened the last time that erosion happened was at the beginning of the England glaciation. It could have happened before then, but let's just say it's the England to form that irregular surface. As you said, because it's a fluvial environment, that it's gone backwards and forwards between a shallow basin and an estuary. So we get the first Woolstonian deposit. The way that I've aligned this Baggington sand is because the elevations of the sediments that were dated through the luminescence process, that matches up. It's just around a mile away, 2 miles away, at a similar elevation. There's no radical changes in the topography between these two, and they've taken the sand out at various places, and it'll look very similar. So Baggington sand. Then we've got the lower Woolstonian clay. So we've gone from that glacial fluvial into a lacustrine environment. So that glacial fluvial is more of a yellow coloured sand, yellowish brown coloured sand. And then we've got sharp change into quite a different coloured sediment that's behaving in a different way. And that's just an illustration of what it looked like in one of the excavations. So that Baggington sand at the base, that you can see that it's collapsing at the point where you've got the water table, and then about a metre of the lower Woolston clay, and then the Woolston sand above, which is more of a silt fine sand. And it's that one where it's around 4 metres thick above that that's got the patterns in it. So that's again the Woolston sand with different types of different sequences of deposition within it. You see it stands up almost like a clay, whereas the glacial fluvial sands don't. Then we've got the odd glacial fluvial channel that cuts through the Woolston sand and clay. And then we've got some more glacial sand on top of it, and we've got the odd ice advance, because again, when we think about glaciation, we think about it's just one out and back, but it just does go backwards and forwards. And so there's odd areas of glacial till being deposited. And so again, when you look at the two types of sediment, there's no way that they could have come from the same place. So these are reworked Anglian deposits, probably from North Wales, the same as the Baggington stand below it. And then we've got the last Woolstonian clay glacial till deposited on the top of it. That's at the top of the sequence at Balsall Common. It might be the Oadby till, but I didn't see any chalk in it. Then you get the melt, and it erodes that nice sequence and drops different channels in it, and those channels that are coming perpendicular to the ridge cut through the finer sand and lower Woolston clay, creating drainage paths. And you've got a bit of periglacial, I think, active slides going on. So they don't leave any solifluction type features on the hillside, but they've cut through the gullies. They've cut through the various sequence on the side of the hill as you've had the melting into the southeast, into the Lake Harrison. Then HS2 comes along and carves a line perpendicular to the gullies. And you've got different, as you can imagine, the phrase on HS2 about perched water is water that's held up. So water's held up on top of the Woolston sand, and any of these glacial till deposits that are somewhere within the sequence. So it's what is the water table. So on one of those photographs of the excavation, you've generally got the lowest held up water table on top of the Mercia mudstone that's below the lower Woolston clay. So because there's, even though we've had such a wet 18 months, there wasn't any artesian pressure when we dug below the Woolston clay. So there is some capacity for any seepage in the water that's held up above it to make its way through those channels, rather than having to pump it out. And whenever you want to modify any consents, it can take 6 months or more to get it modified, if you're lucky. So you can imagine on any earthworks project where there's a lot of plant, it's very expensive. So what can we do to say, this is what we understand the ground model to be. This is why we think we're right. And this is how we think the water can be moved. So we're not creating any new water. We're just demonstrating that the existing groundwater sequence, how that moves down to the lowest level above the Mercia mudstone. And through doing that, we didn't have to say we need new consents or any change to the abstraction, because there's, as it was considered to be a dry cutting, change to that abstraction license on volume again causes long program delays. So by understanding that glacial sequence and how those gullies formed was how we got permission to carry on with the cut without getting any further consents. So some of these gullies can be quite interesting. So in the bottom right hand corner, ignoring the 6C engineered fill, gloves for reference. You might see my gloves a lot. You've got the Woolston sand. Then you've got a gully being cut through it. Then you've got some glacial fluvial deposit on that, a couple of different types of glacial fluvial. Then you've got another gully that's cut across it, and that looks like a glacial till, but it's only in the gully. So it's more likely to be an active slide deposit that's then become over-consolidated through being desiccated through periglacial freezing. So it was notable that the lower Woolston clay was a firm clay, but then on top of that, you'd got a stiff to a hard clay as soon as you went into what I think are the active slide deposits in the gullies. And then you've got the four collapse shears. So the Thor collapse, that's in primarily a sand, whereas in the other part of the Woolston sand that had a lot more fine sand and silt, the Thor shears only appeared to be confined to that material, whereas here we're seeing it in more of a fine to medium sand. So this is the sand above the Woolston sand, and you see that it's behaving quite differently when it's wet, so similar to the Baginton sand beneath it. And just to show the two different sediments side by side, but both with sort of channel-like deposits in it. And there's no way that you'd pick that up with ground investigation. But it helps when you walk around a cutting and you see these different features and you start to reevaluate the ground model. So in summary, there's value engineering opportunities to be on site. Engineering geology isn't just at the beginning of a project or doing the ground investigation or doing hazard mapping. We do some earthworks and slope stability analysis, but we can also be there to give insight during the construction phase support to say, if you do it this way, you're going to save yourself millions because you're not having to wait a year for consent. And that's what happened here. Engineering geology is primarily an applied science, and we couldn't work without the work of pure geologists and the research that they do. And so it's up to our job, it's up to us as individuals to read their work and apply it, because it can have a significant impact. Observation skills, do the basics, go out and have a look, practice what you were taught if you did geological mapping or engineering geology mapping or geomorphological mapping, anything. Go and improve your observational skills, because there's so much just under your nose. We do get kind of carried away with digital displays and having things on smartphones or tablets and always access and always networks to things. But the basic thing of just looking what's there, practice it. And that kind of goes back for your research. Just because somebody's done a desk study before, there's no harm in you picking the books up at whatever stage of a project and reevaluating what somebody else has done. Geological maps, as we kind of said within this, they're a starting point. And if anybody does any sailing, when you switch on a chart plotter, there's a sign saying, don't believe what I'm about to tell you. So people still need to have paper charts, because if you get into difficulties, then they just say, it's not my fault. And BGS do the same thing, and why not? Groundwater is everything in construction. The cost of moving it, the cost of changing plant to manage it, any construction delay, even for a day, can cost tens of thousands. And engineering geologists can be applied at any stage to reevaluate what's been done. So I'm pleased I've had the opportunity to do engineering geology and apply it on this and other projects. All the various references, and I was looking for some jokey things. So engineers, people who solve problems that others didn't know existed. I'm sure you'll feel like that when you're trying to explain something to somebody and saying, what are you on about? And then, as I say, you're trying to arrange something that to happen that's usually complicated or difficult. But it all stems back to that original thing of going back to your starting point of your education and your observation skills and applying them. That's it. Thanks.